we are living through, I mean, just an incredible moment right now. These large language models, LLMs, things like ChatGPT, they've just exploded completely.
It's everywhere.
And they're fundamentally changing how we interact with information, even how we work.
Yeah.
I mean, think about that growth rate hitting an estimated 100 million monthly users in, what, 2 months?
It's staggering, faster than almost anything we've seen before online.
Right.
And it really is remarkable how fast these things moved from, research labs into everyday life. They're pushing boundaries that seemed years away just a short while ago.
Absolutely. And for this deep dive, we've pulled together a stack of source material. We've got excerpts here from a couple of documents that really promise to take us under the hood of these LLMs.
Yeah, we're not just scratching the surface.
No way.
Yeah.
We want to get into their core mechanics, how they actually learn, the really clever ways people have figured out to guide them.
And control their behavior.
Exactly. And how people are building pretty sophisticated applications with them now. And yes, even the tricky part, how we try to figure out if they're actually doing a good job.
Evaluation, that's a big one.
So our goal here really is to take these sources, pull out the most important nuggets, the key takeaways, and give you a bit of a shortcut.
Yeah, a shortcut to understanding what's foundational, what's, really driving these powerful systems.
Consider this just a conversation for you, helping you navigate this really complex topic
Yeah.
without getting sort of bogged down in all the jargon.
Okay, let's do it.
So let's just dive right in. At their absolute core, what is an LLM actually doing?
Okay, fundamentally, at the very bottom layer, an LLM is trained to do one thing: predict the next token in a sequence based on the tokens that came just before it.
The next token,
Yeah.
like the next word. That sounds almost too simple for the kind of things they produce.
It does seem that way, doesn't it? But they do this prediction task on an absolutely massive scale. Think of them less like creative writers and more like incredibly sophisticated statistical mimics.
Mimics.
Yeah, they've learned patterns from vast amounts of text, and they calculate the most statistically probable continuation of whatever text you give them the prompt.
Okay.
The sources have a good example. If you give an LLM, say, yesterday my TV stopped working, now I can't turn it on at...
It would probably say all.
Exactly. All, because statistically, that's the most likely completion it's seen in its training data. That's the core prediction task.
Okay, that makes sense. Simple task, but massively complex execution. Now, you said token, not word. How do they actually see the text?
Right, good point. They don't process text letter by letter the way we read. They break it down first into these bite-sized chunks called tokens.
Tokens. And that's a pre-processing step.
Yeah, it's called tokenization. It's crucial.
And I remember the sources mentioning this can lead to some weird quirks, right?
It really can. Because they work with these predefined tokens, not individual letters, tasks that seem simple to us, like reversing a word or even just consistently handling capitalization.
Yeah.
That can be surprisingly hard for them.
Huh. Like A versus A.
Exactly. The sources note that A and A might be completely different tokens. So while the model might learn that the token for Apple relates to the token for Apple, the difference in the tokens themselves can make tasks like, say, changing case throughout a document much harder than you'd intuitively think.
That's fascinating. Something so basic looks different to the model. Okay, so tokens are the input. What's the engine processing them? The sources use this analogy. Mini brains.
Yeah, the transformer architecture. That's the foundation for pretty much all modern LLMs. And the analogy they use is that it's like having thousands of identical mini brains.
Wow.
Conceptually, imagine one sitting on top of each token position in the sequence.
Thousands of them. What are they all doing?
Each one is trying to understand the document, but from the perspective of its own token position. And they do this by passing information through multiple layers, refining their understanding at each step.
Okay.
But here's a key constraint. The causal mask. Each mini-brain can only see information from tokens to its left.
Ah, so the mini brain at token 5 only sees tokens 1, 2, 3, 4, and 5. It can't peek ahead.
Precisely. No peeking ahead. And this connects back to that prediction idea and also something we'll get to later. The output from the highest layer of the very last mini-brain that's the predicted next token, that prediction, then becomes the input for a new mini-brain at the next position in the sequence.
Ah, okay. So it predicts token 6, then a new mini brain looks at tokens 1 through 6 to predict token 7, and so on.
Exactly right. It's this iterative process. The output of one step feeds the next. And that mechanism is related to how these models can sometimes appear to think aloud when we prompt them in certain ways.
Got it. Okay, so we have the basics. Next token prediction, tokens as input, and these layered transformer mini brains processing sequentially. How do they actually learn all the stuff needed to make those predictions work so well?
Right. That comes down to training, and it typically starts with something called pre-training.
Pre-training. What does that involve?
So in deep learning generally, pre-training means you take a neural network and you optimize it on a really broad general task using a massive data set. Before you then adapt it or fine-tune it for more specific things,
Right.
the core idea is that a model pre-trained on, say, predicting the next token across vast swaths of the internet learns an incredible amount about language structure, facts, common sense, you name it.
So it builds a general foundation.
Exactly. And that general knowledge makes it much, much easier to then train it for specific tasks later, often needing way less task-specific labeled data than you'd need if you started from scratch.
So you don't need like a separate giant data set for every single application.
Pretty much. It makes developing these more general, capable models feasible. And the sources actually talk about pre-training in NLP more broadly first, not just the generative models we see now.
And they mentioned self-supervised pre-training. Why is that important?
Self-supervised is key because the supervision, the signal telling the model if it's right or wrong, comes from the data itself. You don't need humans labeling everything. For transformer models, the specific self-supervised task often depends on the architecture. For decoder-only models, like the GPT family.
The ones that just predict the next token.
Right. The task is that standard language modeling predict the next token given the previous ones.
Okay. What about other architectures, like encoder only?
For encoder-only models, the classic example is BERT. It uses something called masked language modeling, or MLM.
Masked language modeling. What's that?
Imagine you take a sentence and you just blank out or mask a few words. BERT's job is to predict those masked words, but crucially, it gets to see the context from both sides left and right of the mask.
Oh, okay. So it's not just predicting the next word, it's filling in blanks.
Exactly. The sources describe how BERT uses special tokens like CLS at the beginning and SEP to separate sentences, partly for this MLM task and also for another task it was trained on, next sentence prediction.
NSP. Predicting if one sentence follows another.
Yeah. Though interestingly, later research, like with the Roberta model, found that just removing that NSP task and scaling up the MLM training with more data and a bigger model actually improved performance, or at least didn't hurt it.
Huh. So doing a simpler task, but just bigger and better, was more effective.
That was a really important finding. It suggested that sometimes the path to better performance isn't necessarily adding more complex training objectives, but just scaling up much bigger models, much more data on these simpler, robust, self-supervised tasks. Scale turned out to be incredibly powerful.
Wow. Okay, so pre-training builds this massive general foundation of knowledge through self-supervision. What's the next step to make it useful for specific things?
That's where fine-tuning comes in.
Right.
You take your pre-trained model and you continue the training process, but this time you train it specifically on the downstream tasks you actually care about.
Right.
The goal is usually to maximize the probability of the model generating the correct output for a given input on that specific task, building on that pre-trained knowledge.
And what kinds of tasks can you fine-tune for?
Well, for models like BERT, fine-tuning makes them good at things like text classification. You might use the final representation of that CLS token as a summary for classifying the text. Or they can be fine-tuned to act as the encoder part of a larger system, like in machine translation.
Is fine-tuning always about retraining the whole massive model?
Yeah.
It sounds expensive.
It can be, but there are more efficient methods now. The sources highlight one called LoRA, which stands for low-rank adaptation.
LoRA. Low-rank adaptation. What's the idea there?
Instead of tweaking all the billions of parameters in the pre-trained model, you freeze most of the original model and only train a very small number of new parameters. Think of it like adding little adapter layers.
So much more efficient.
Way more efficient. Less compute, less memory. The intuition, according to the sources, is that LoRA isn't really teaching the model brand new facts or complex reasoning from scratch. It's more about teaching the model how to access and apply the vast knowledge it already learned during pre-training, but specifically for the new task's format or style. It's great for adapting the output format, the tone, getting the feel right for a specific domain without that full retraining cost.
Got it. Pre-training builds the potential. Fine-tuning adapts it, sometimes very efficiently with things like LoRA. But okay, when we sit down to actually use one of these models, how do we tell it what we want right now?
That brings us to prompting. The prompt is just, The input text you give the LLM, that's X in the technical notation.
That X, and that guides the output, the Y.
Exactly. The prompt acts as the condition for the generation. It tells the model what kind of you're looking for. We often use prompt templates to text with placeholders you can fill in, like asking for weekend suggestions for this specific city.
Just giving it direct instructions seems like the simplest way.
Yeah, that's instruction-based prompting. Adapting the model on the fly just by telling it what to do. The sources use sentiment analysis as an example. You just give it the text and maybe a label like polarity and expect it to fill in positive or negative.
Okay, but sometimes instructions aren't enough.
Right. That's where in-context learning, or ICL, comes in. This means you include examples, demonstrations of the task directly inside the prompt.
Showing it what you want right in the input.
Exactly. There's zero shot, which is just the instruction, relying on the model's built-in abilities from pre-training or fine-tuning. Then there's one shot or few shot. Here, you include one or maybe few examples of the input and the desired output formatted correctly right there in the prompt before your actual query.
Why add examples?
Well, sometimes zero shot just doesn't work well. Or maybe you want to shape something subtle, like the persona. If you want it to respond like a, I don't know, grumpy movie critic, a few examples of grumpy reviews can steer it that way much better than just instructions.
Makes sense.
But there's a catch, the sources point out. Few-shot examples can sometimes make the model pick up on spurious patterns. Like, if your examples accidentally list things in alphabetical order, the model might assume all lists should be alphabetical, even if that wasn't intended.
Unintended consequences.
Yeah, so few-shot is often best when the example shows something that's hard to explain just with words.
Right. You have to be careful what signals you're sending. Okay, what about chain of thought? Cup prompting. That feels like a really big deal lately.
Oh yeah, COTI is huge. Chain of thought prompting is basically insisting that the model outputs a step-by-step reasoning process before it gives the final answer.
Is that connected to that thinking aloud idea you mentioned earlier with the transformers?
It absolutely seems related. The intuition is, even though these models don't really think like humans, forcing them to externalize the steps to generate that reasoning trace actually helps them arrive at better answers for complex tasks.
Like math problems.
Math is a classic example. The sources show prompts like, let's think step by step. But other phrases work too, like, let's think logically. And code isn't just for math. It helps with logical reasoning, common sense problems, even symbolic manipulation or code generation.
Interesting. What other prompting tricks are there?
Well, there's problem decomposition, breaking a big, complex problem down into smaller, manageable subproblems.
And the LLM tackles each one.
Sometimes sequentially in one go, or sometimes you might have the LLM call out to external tools, like using a calculator function for the math parts.
So the LLM acts like an orchestrator.
In a way, yeah. Another really important technique is providing reference information. This is often called retrieval augmented generation, or RGAE.
RGAE. I've heard that acronym.
The idea is you first retrieve relevant documents or snippets of text, maybe from a search engine or a specific database, and then you include that retrieved text in the prompt along with your question.
Giving it the specific context it needs.
Exactly. It helps ground the model's answer in factual information. The prompt might look like, based on this context information, retrieve text, answer the following question. And you can even instruct it to only use the provided context if accuracy is paramount.
Okay, what else?
There's self-refinement. You basically prompt the LLM to critique its own first attempt and then generate an improved version. It's related to self-reflection. The sources mention a method called deliberate then generate, DTG, as an example.
Asking it to double-check its work.
Sort of, yeah. And then there's ensembling, combining multiple predictions.
How does that work?
You can do it in a few ways. Use multiple different LLMs for the same prompt, that's model ensembling. Or use one LLM but try slightly different prompts, prompt ensembling. Or just ask the one LLM to generate several different possible answers for the same prompt output ensembling.
And combine them somehow.
Right. You can even mix and match these techniques to get more diverse and hopefully more robust results.
Man, putting together a good prompt sounds like an art form. How do you structure all these pieces?
It definitely involves some craft. Prompt structure is key. The sources describe prompts almost like documents. Sometimes they use a metaphor of a play script or a transcript with alternating roles like user and assistant.
Okay.
They also mention these special reserved tokens, like imstart and amend, that chat APIs use. These aren't just formatting, they're crucial for separating turns and preventing users from injecting text that might confuse the model or make it think it's a system instruction.
Ah, preventing prompt injection.
Exactly, that's
Yeah.
part of it. For really long prompts with lots of context, the sandwich technique is often recommended.
Sandwich technique.
State your main goal or instruction clearly at the very beginning and repeat it at the very end. This helps keep the model focused, especially if there's a lot of information packed in the middle.
Okay, beginning and end.
And using structured formats within the prompt, like XML or maybe YAML, can sometimes help the model parse complex information. This follows the Little Red Riding Hood principle. Use formats that the model likely saw a lot during its pre-training on web data. If it saw tons of XML, it's probably pretty good at understanding XML structure. The sources show an Anthropic example using custom tags like ant thinking and an artifact.
Got it. Stick to familiar structures.
Mm-hmm.
And managing all the context you might want to put in the prompt.
Right, prompt assembly. You need to gather the relevant info, the context or artifacts, break it down into snippets, figure out what's most important, and then somehow fit it all within the model's token limit, its context window.
The token budget.
Yeah. The sources talk about greedy approaches, either adding the most important stuff first until you're full, or maybe starting with everything and removing the least important stuff until it fits.
And there's that issue with long prompts.
Ah, yes, the Valley of Meh. It's an observed phenomenon where models sometimes pay less attention to information that's buried deep in the middle of a very long prompt, compared to the info at the beginning or the end.
The Valley of Meh. I love that. Okay, so location matters inside the prompt too. This prompting is all about guiding the model for a specific task. But the sources also talk a lot about alignment. How is that different?
Good question. Prompting is task-specific instruction. Alignment is broader. It's about shaping the model's overall behavior to align with human intentions and values.
Like making sure it's helpful, honest, harmless.
Exactly, making sure it's accurate, unbiased, truthful, refuses harmful requests. The example given is an LLM refusing to generate instructions for something dangerous. Alignment is fundamental for using these things responsibly.
So how do you achieve alignment? Is it just more fine-tuning?
Instruction fine-tuning, which we already discussed, is definitely part of it. It helps the model learn to follow instructions generally. And there was that surprising finding that even a small amount of instruction data can sometimes unlock complex abilities.
Right, the superficial alignment hypothesis.
Exactly. The idea that the core skills are learned in pre-training, and the fine-tuning just teaches the model how to use those skills in response to instructions.
But there's more to it.
Oh, yeah. The really big one, the method everyone talks about for serious alignment, is reinforcement learning from human feedback. RLHF.
RLHF. Okay, that sounds complicated. Walk me through it.
It is a multi-step process. The sources often show a diagram. Step 1, you start with your base LLM, maybe pre-trained and instruction fine-tuned. This is your initial policy in RL terms.
I'll get the model.
Step 2, you collect human preference data. You take a bunch of prompts, have the model generate several different possible responses for each prompt.
Multiple answers.
Right, maybe 4, maybe 9, the sources suggest. Then you show these responses to human labelers and ask them to rank them from best to worst for that prompt.
So humans are the judges of quality.
They are. Step 3, you use all that ranking data to train a separate model called a reward model.
A reward model, what does that do?
Its job is to learn what kinds of responses humans prefer. It takes a prompt and a response and outputs a score or reward indicating how good it thinks that response is based on the patterns it learned from the human rankings. The sources mentioned it's often trained on pairs of responses from the human data.
Okay, so it learns to predict human preference.
Exactly. Step 4, you use that reward model to further fine-tune your original LLM, the policy, using reinforcement learning algorithms.
How does RL fit in?
The LLM generates text, takes actions, given the prompt, the state. The reward model provides the reward signal. The LLM is trained to maximize the expected reward, basically, to generate text that the reward model predicts humans will like.
So the LLM learns to please the reward model, which learned from the humans.
That's the loop. The sources mentioned PPO proximal policy optimization is a common RL algorithm used here. They also mention some challenges.
Like what?
Well, rewards can be sparse. You often only get a score for the whole generated sequence, and there's a risk of over-optimization or reward hacking.
Reward hacking.
Yeah, the LLM might find ways to get a high score from the reward model without actually producing helpful, honest, harmless output. It finds loopholes. So you often have to mix the RL training with samples from the original base model to keep it grounded.
Wow, that is a really sophisticated dance to get these models behaving properly. Okay, so with all this power prediction, learning, prompting, alignment, how are people actually building more than just chatbots? How do you build complex apps?
Right. That takes us into the realm of agents and workflows. The sources make a distinction here. Agents are more than just LLMs answering questions.
Up so.
Agents are designed to leverage LLMs to manage workflow execution. They make decisions, act reliably, figure out when they're done, and potentially even correct themselves.
Okay, so more autonomous. What are the key features?
The sources list things like managing a workflow, making decisions about next steps, acting proactively, recognizing task completion, and handling failure, maybe by correcting or halting.
And how do they act?
They need tools. Agents are typically given access to a set of tools they can call to interact with the world or access external information.
What kind of tools are we talking about?
The sources suggest categories: data tools for getting info, like web search, database queries; action tools for doing things, sending emails, updating a CRM; and communication tools for interacting with the user, asking for clarification, presenting choices.
Are there best practices for designing these tools?
Yeah, the sources offer some guidelines. Limit the number of tools available at once. Make sure they cover distinct functions. Avoid overlap. Keep the tools relatively simple. Don't just wrap complex web APIs directly. And crucially, keep the arguments the tool takes simple and use standard types like JSON. Apparently, good documentation on how to represent these tools effectively in the prompt for the LLM is sometimes lacking, which is a challenge.
So the LLM needs to understand the tools it has. How does it learn to use them with reasoning?
There's a pattern called REACT, which stands for reason plus act. The idea is to structure the interaction, often within the prompt's history, by interleaving steps. The model generates a thought, explaining its reasoning, then an action, specifying which tool to call and with what arguments, and then it processes the observation, the result that comes back from the tool.
Thought, action, observation. Like it's narrating its process.
Exactly. It makes the reasoning explicit. The sources give examples with hypothetical search or lookup tools. Interestingly, they note that early experiments showed React didn't work well unless you included examples of this thought-action observation flow directly in the prompt. The model needed to be shown how to do it.
In-context learning again. And agents need to keep track of stuff, right? Context.
Definitely. They need static context, like their initial instructions, dynamic context, like the user's requests and the conversation history, and the results from tool use those observations. This often gets organized as artifacts presented to the model in the prompt.
Seems like things could go wrong with agents acting in the world.
Safety. Absolutely critical. That's where guardrails come in. These are mechanisms to manage risks.
Like what kind of risks?
Data privacy, preventing the agent from leaking sensitive info. Reputational risk, making sure the agent acts appropriately, stays on brand, doesn't generate harmful stuff.
How do guardrails work?
They can be applied at different stages. Filtering user input, scrutinizing tool use before execution, intercepting dangerous requests, or triggering human oversight.
Bringing a person in, when would that happen?
The sources suggest triggers like if the agent fails repeatedly, if it tries a high-risk action like canceling an order or issuing a big refund, or if confidence scores drop too low. Human in the loop is key for safety.
Okay, so agents are about dynamic interaction using tools.
Yeah.
What are LLM workflows then? How are they different?
Workflows generally trade some of that agent flexibility for more reliability on specific complex tasks. The idea is you break a big task down into a sequence of smaller, well-defined subtasks.
Like an assembly line.
Kind of. And there's a supervisor process, which could be an LLM or just regular code that coordinates these steps. Workflows are typically designed for one specific job, not arbitrary user requests.
And the steps themselves? Can they use LLMs?
Yes, that's the interesting part. Individual tasks within the workflow can be traditional code, or they can be calls to an LLM. The key is that each task needs very clearly defined inputs and outputs so they can be chained together reliably.
Can you use an LLM for a step that isn't just like writing text?
For sure. You could have an LLM task designed to extract structured data from unstructured text. The sources give an example. An LLM step reads some HTML, identifies restaurant details, and then uses a structured function call, like save restaurant data database, to output that data cleanly for the next step.
Right.
Enforcing structured outputs via function calling is important here.
And can workflows self-correct too?
Yes, techniques like reflection are mentioned. This involves having the application layer outside the LLM analyze the output of a step. Does it meet the requirements? If not, the workflow might loop back and prompt the LLM again, maybe asking it to refine its previous output based on the detected error.
It's clear there's a lot more engineering involved in building real applications than just chatting with an API, which leads perfectly into the final big topic, evaluation. How on earth do you know if any of this stuff is actually working well? It sounds hard.
It is hard. So many variables, right? The model, the prompt, the context, the tools. The sources break evaluation down into two main categories, offline and online.
Offline is testing in the lab before real users see it.
Exactly. Testing in a controlled environment. One core technique here is using example suites.
Example suites, like test cases.
Similar, but maybe more flexible than traditional rigid software test suites. You gather a set of representative examples, maybe real historical data, maybe logs of past interactions, maybe even synthetic data you create. Then you run your prompts or your agent logic against this suite systematically.
What's the goal?
To see how it performs on typical inputs, identify common failure modes, observe shortcomings. The sources use a cool example about summarizing GitHub pull requests. They use an example suite, saw the summaries were often too short or too long or made weird assumptions, and then they iterated on the prompt based on those observed patterns.
So it's systematic, but also lets you see the nuances.
Exactly. You can find examples from your own logs, or if you're building something common, maybe find relevant public data sets, like using GitHub code itself if you're building a coding assistant.
Okay, you run the examples.
Yeah.
How do you check if the output is actually good?
Several ways for offline assessment. If there's a single right answer, you can do a ground truth match, compare the output directly. Easy for numbers or classifications.
But not for generated text.
Right. For more complex outputs, you might use a functional test. Isolate some critical aspect you can automatically check. For generated code, can you run unit tests on it? Does it compile?
Makes sense.
And then there's the idea of using an LLM to evaluate the output of another LLM.
Can that really work? An LLM grading itself?
The sources acknowledge the potential issues, but suggest it can work if you do it right. They introduce a framework called SOMA assessment.
So?
Specific questions, ordinal scaled answers, and multi-aspect coverage.
Okay, break that down. Specific questions.
Instead of asking the evaluator LLM a vague question like, is this good? You ask very specific things. Is the summary factually accurate according to the source text? Is the tone appropriate? Does it follow the requested format?
Got it. Ordinal scale.
Use a rating scale, like 1 to 5, for each specific question. Easier for the LLM to handle than open-ended critique.
And multi-aspect.
Cover different dimensions of quality that you care about: accuracy, relevance, coherence, safety, etc. Don't just ask one thing.
SOMA. Specific, ordinal, multi-aspect. Okay, that's offline. What about testing with real users?
That's online evaluation, testing in the wild. The huge advantage is you see how it really performs under real conditions with real user behavior.
But downsides?
Less control, obviously. Getting a clear signal can take much longer. You need really careful experimental design, A/B testing, usually, with proper random assignments so you know the difference you're seeing is actually due to the change you made.
And what do you measure online?
A few categories of metrics. Direct feedback is the obvious one, thumbs up, down buttons. The sources mention the ChatGPT feedback and note that user frustration is often a very reliable signal.
Yeah, I bet.
Then there's functional correctness. Did the thing the LLM suggested actually work in the real world? User acceptance. Did the user actually click the suggestion or use the generated text? Achieved impact. Did using the feature actually help the user achieve their goal faster or better? And finally, incidental metrics, things you measure around the interaction that might correlate with quality.
So lots of ways to measure.
Yeah, but the key point for online is, because you have limited bandwidth, you can't test everything all the time, you need to be very deliberate and focused in your online experiments.
This has been, wow, a really deep dive. We've gone from the absolute basics, predicting tokens, the transformer mini brains,
Through pre-training, fine-tuning, LoRa.
and all those prompting techniques, ICL, COT, RA, and the whole complex world of alignment with RLHF.
And building actual applications with agents, tools, workflows.
And finally, the challenge of just figuring out if any of it works, using offline and online evaluation.
It really highlights that even though these models seem magical sometimes, they're incredibly complex systems, we're still, figuring out how to reliably steer them and use them effectively.
And really understanding all these layers for the tokens right up to the prompt strategy and the evaluation metrics It feels fundamental if you're going to work with LLMs or build things on top of them.
Absolutely. And the sources definitely hint we're just scratching the surface. Improving reasoning, making training more efficient, handling multimodal data like images and video. There's still so much active research.
Yeah, it's fascinating how much these models are shaped by the data they learn from, basically, the reflection of the text we put out into the world.
They learn the patterns they see.
Which kind of leaves us with a final thought for you, the listener, to maybe chew on. Since LLMs learn primarily from the patterns in the data we create and share online, what kind of intelligence, what kinds of biases, and ultimately what kind of future capabilities are we actually building for them, perhaps inadvertently, through our collective digital footprint?